Modern battle spaces are complex, multidimensional environments that extend beyond traditional land, sea, and air domains where integration of advanced technologies are critical to enhance situational awareness and improve decision-making. Drones are crucial in a battle space for their versatility, real-time intelligence, and risk reduction. They provide persistent surveillance, enabling commanders to monitor enemy movements and assess threats without endangering personnel, allowing access to dangerous and hard-to-reach environments, extending the reach for military operations. Drone swarms are groups of unmanned aerial vehicles that operate together as a coordinated unit, using advanced algorithms and communication systems to behave like a single entity. They can overwhelm enemy defenses, conduct large-scale reconnaissance, or execute simultaneous attacks, complicating the enemy's response. Swarms are adaptive, resilient, and capable of performing complex tasks collectively, making them highly effective in diverse military applications. Additionally, they offer scalability, redundancy, and cost-effectiveness, allowing missions to continue even if some drones are lost. For this demonstration, we have developed control algorithms for a leader-follower UAV swarm that can perform synchronized flying, foraging for object detection, and inter-UAV obstacle avoidance to ensure safe swarming operations. First, let's look at our UAV testbeds. We have used a hexacopter configuration for its enhanced payload carrying capability. On the drone, we have an onboard computer that is responsible for the swarm control algorithms and both inter-UAV and ground UAV communications. We also have a software-defined radio that works as the radio unit for wireless communications. The first maneuver that we have designed is to show swarm synchronization, where we have a leader following a pre-planned trajectory. The follower gets position and velocity updates from the leader and utilizes that information to position itself at an offset from the leader drone. We shall revisit this test to observe the impact of information latency on swarm responsiveness. In the second maneuver, the swarm is performing foraging, where the leading and following UAVs hover in sync to survey a designated area of importance. In this case, the two UAVs follow a square-shaped area of interest, where the leader dictates the points of interest. The follower drone then follows the leader drone around this square-shaped area of interest. Such maneuvers are critical to performing intelligence, surveillance, and reconnaissance operations. With an accompanying ISR payload, the swarm can segment a large region into smaller sections and search for objects of interest simultaneously, significantly lowering the amount of time taken to complete mission objectives. The last maneuvers we have designed to illustrate the obstacle avoidance feature of our drone. Every drone in the swarm has an imaginary bubble surrounding it, and if it detects that another drone in the swarm has breached this bubble, it takes evasive action according to pre-programmed logic. Here, Drone 1 has been programmed to hover at single point. Drone 2 has been forced to take a path that overlaps with Drone 1. The drones do not proceed with their mission until they perceive that a collision has been avoided. Information freshness is critical to ensure that each drone has the latest updates from its fellow swarm members. Now let's look into the system that enable inter-drone communication. Effective communication within a swarm allows drones to share information, make collective decisions, and adapt to changing conditions in real time. Latency and scalability are two key components that define the efficiency of a swarm. Real-time coordination requires low-latency communication, ensuring that drones can react quickly to changes. Traditionally, ad hoc networks are used, which are spontaneously formed and do not rely on fixed infrastructure. The first iteration of our UAV swarm used a similar ad hoc network that was built on top of a Wi-Fi IBSS platform. While such a network maintains low-latency communication, it cannot operate effectively in beyond visual line of sight conditions and responds poorly to swarm scalability. For this demo, we have developed a UAV platform that allows for communication over a private 5G network. Basing our communication system on a 5G network enables us to use pre-existing infrastructure to operate in beyond visual line of sight conditions effectively. To accomplish this, we have enhanced our onboard computers from a Raspberry Pi to an x86-based Intel NUC computer. We have also incorporated a USRP B210 acting as the radio unit. We have designed the system to do message exchange between the leader and follower UAV through a ground-based G-Node using the UU interface. We are going to use the synchronization test from earlier to demonstrate the impact of reduced subcarrier spacing on the responsiveness of our UAV swarm. In this first case, we utilize an uplink and downlink subcarrier spacing of 15 kHz. In this satellite view overlay, we can see the leader UAV in the center with follower 1 on the right. We are going to plot the packet round trip time in blue and ground distance between the leader and follower 1 in red. Now when we begin the synchronization test, we see a sudden increase in the inter-UAV ground distance once the leader starts moving. When the leader reaches the end of its run, it waits for the followers to catch up, resulting in the decrease in inter-UAV separation. Ideally, we want the separation to be constant. This sudden increase in inter-UAV distance is an indication of high round trip time between the leader and follower drone. In this test, we see round trip time between 200 and 300 milliseconds, resulting in poor swarm responsiveness. Collision avoidance also fails to work properly in situations with high latency due to lack of leader position information freshness, as seen from this clip where the follower UAV had older position information, resulting in the collision avoidance maneuver not being activated, resulting in a near collision. Now we have increased the uplink and downlink OFDM subcarrier spacing to 30 kHz. First and foremost, we see a drop in the packet round trip time. We can see at least a 50% drop in the round trip time, where the current round trip time ranges between 120 and 140 milliseconds. The impact of lower latency on the inter-UAV distance is obvious. Now we see significantly lower variance in the inter-UAV separation, indicating that the swarm is performing much more responsively. In this demonstration, we have shown the capabilities of our uniquely designed distributed decision for autonomous UAV swarms and their ability to perform synchronized tasks to achieve mission objectives. We have also demonstrated the ability of the swarm to track other aerial vehicles and perform self-swarm maneuvers to avoid collisions. We have developed a 5G-based communication system for drone-to-drone communication and have characterized the impact of latency on swarm reactiveness. Thank you for watching.